So, good afternoon, everyone. Today, I welcome you all for our online seminar series titled as Advances in Quantum Theory and Its Frontiers. As many of you know that the year 2025 has been declared by UN as the International Year of Quantum Science and Technology. And this marks the centenary of the advent of quantum mechanics. In a simplest way, one can describe the theory of quantum mechanics as the theory which explains correctly the physics of subatomic particles. So around the beginning of 19th century, the quest for correct theory that explains the physics of subatomic particles began. And then several renowned physicists uh, worked on the directions, because at that time the theory of classical phenomena was not describing all the theories that people are getting. So for example, here we have the black body radiations, photoelectric effect, Bohr model, the Stankalak experiment. And then in 1925, the foundations of quantum theory were solidified, which gave birth to the direction of modern quantum mechanics. And since then, several research works has been done, and this quantum theory people have applied on the quantum communication, to the communications, computations, and this gave birth the theory of quantum information and computation. One of the highlight is that in 2022, this Alan Aspect, John F. Clauser, and Anton Zeilinger, they won the Nobel Prize in physics for the experimental verification of Bell inequalities, which is a cornerstone in the quantum information science. And so to mark the birth of 100 years of quantum mechanics, we have launched our online seminar series with the collaboration of the Department of Physics, IIT Hyderabad. And our idea is to bring several eminent researchers throughout India and abroad to give the talk in different directions. For example, quantum information, optics and photonics, sensing, computations, interface of many body systems, and many more. We have officially launched a YouTube channel named as Quantum-Talks. So our idea is to put the recorded version of each talk in this YouTube channel. Please do subscribe this one. And now I officially invite Professor Abhinav Tandon, the head of the Department of IIT Mestra, to officially inaugurate this program.
Okay, thank you, Dr. Anandita. Okay, I welcome you all in this seminar on advances in quantum theory and its frontiers, a collaborative effort between our institute, IIT Mesra, and IIT ISM Dhanbad. First of all, I would like to thank our VC, Professor Indranil Manna, who gave his consent to conduct this seminar. I also express my deepest gratitude to the team of IIT ISM Dhanbad, head of physics department there, Professor Bobby Anthony, their faculty members, Dr. Sudipta Singha Roy and Avijit Mishra, who are collaborating with us. As far as I know about quantum computing, I think quantum computing has the potential to revolutionize the approach towards complex problems. And we are all fortunate enough that we have speakers from prestigious institutes who will share their insights on this topic. Okay. As far as today is concerned, this is the second talk in this series, and today's speaker is Dr. S. Chakraborty from IIIT Hyderabad, who is an eminent expert in this field. And I believe that everyone here will be benefit from his talk. Thank you.
So I welcome Professor Shantanav Chakraborty. So here is a brief outline of his academic work. So he finished his PhD in 2017 December from the University of Lisbon. After then, he joined as a postdoctoral researcher in École Polytechnique of Brussels. Then he was an FNRS postdoctoral fellow from 2019 to 21 in the Center for the Quantum Information and Computation. again in University Libre de Brussels. Then he joined IIIT Hyderabad as an assistant professor from 2021, and there he is also in a part of their CQST Center and CSTAR. So he mainly works on the quantum computation and quantum algorithm. So I will stop sharing my slides, and Shantanav, the floor is yours. So
Thank you, everyone. I have some feedback problem, so I can hear myself.
you can hear yourself.
Yeah, so there's a feedback problem, I
Echo.
think. Yeah. So
Echo
somebody
हो रहा है
needs to
बोल.
mute it. I think it's gone now. It's gone
Okay,
now.
okay, because of this. Okay. So you can share your slides, Shantanu.
Yes.
Okay.
Uh, is my screen visible?
Yes, but you need to make it in full mode, in full screen mode.
Yes, and can you also see the laser pointer?
Yes,
This one?
we can.
Okay, so I would like to thank the organizers for the opportunity to speak here. I heard from Anindita that many of the people in the audience are students. So I would, encourage everyone to interrupt me and ask questions if needed. Uh, so this talk is going to be about a recent paper which deals with implementing a technique called linear combination of unitaries, which is a very widely applicable quantum algorithmic technique on intermediate term quantum computers. So these would be quantum computers that are not necessarily fully fault tolerant, but somehow quantum computers that have certain restrictions. So what I'll begin with initially is explaining better what I mean by intermediate term quantum computers, and then move on to this technique of linear combination of unitaries, and then subsequently explain the techniques and my contributions, etc. So the best place to start, in my opinion, is to talk about the era of quantum computing that we are in currently. So this is the so-called noisy intermediate scale quantum era. So you probably, all of you have heard of it. So quantum computers that are present in this NISQ era, they have certain characteristics. Well, these characteristics are that they are limited by noisy qubits. So there are quantum computers of a few noisy qubits. The quantum circuits are short depth and are also noisy. So this is what are the features of the quantum devices that are available today, for instance. And using these sorts of devices, NISQ devices, people have come up with quantum algorithms tailored, essentially to such devices where you have these restrictions. Now, one of the features of the quantum algorithms that have been developed in this NISQ era is that they are heuristic in nature. So what do I mean by this? Well, the algorithms don't have reliable performance guarantees. So provable quantum speedups for useful problems have been very hard to obtain. So people have just designed algorithms which run in a heuristic manner. So on some instances, you see certain advantages. On other instances, you don't see certain advantages, etc. But you cannot prove that the algorithm has certain advantages. So this is what is a characteristic of the current era of quantum computing, which is known as NISQ. So the question then one needs to ask is what comes after NISQ, right? So in that regard, I would request you to look at this plot that I took from the paper by John Preskill from 2018, where Preskill said back in 2018 that within 5 years we would be transitioning away from the NISQ era, right? So that was 2018. So within 5 years means 2023. So we are already past that. We are in 2025. So the question that one needs to ask is what comes after NISQ? So clearly, as I mentioned, NISQ era has been, useful, but we could not really develop quantum algorithms for useful problems with reliable performance guarantees. And on the other hand, a full-scale, fully fault-tolerant quantum computer is probably a long time away. So what comes right after NISQ? So between the fully fault tolerant era and NISQ, what lies? So this is going to be kind of the focus for the next couple of slides. So indeed, this is the question we ask. So the current era of quantum computing is the NISQ era, and say fully fault tolerant quantum computers are going to be some decades away, depending on how optimistic or pessimistic you are. So what comes in the middle? There are many possibilities. One of those possibilities is what are called early fault tolerant quantum computers. So these are quantum computers that do not necessarily have the capabilities of a full scale error corrected quantum computer, in that it still shares some characteristics with NISQ, but with important differences. So let me elaborate a bit on this. So these would be quantum devices or quantum computers which would still have short depth quantum circuits, just like NISQ. But the key difference is that you would now have a limited number of logical qubits. And what this means is that the number of qubits, that total number of qubits that you have access to, are going to be limited. So you would have very few ancillary qubits, for instance. But nevertheless, these would be logical error corrected qubits. So it is not fully fault tolerant in the sense that you don't have access to unlimited number of ancillary qubits, very deep quantum circuits. But nevertheless, you have some notion of fault tolerance on a restricted sized quantum computer. So these are the so-called early fault tolerant quantum computers. And so if you now try to hone into this concept a bit more, what we realize is that quantum circuits of this kind are not allowed in the early fault tolerant era. So what do I mean by this? If you look at this representative quantum circuit, it requires m ancillary qubits. So essentially many ancillary qubits. It requires implementing a circuit that is quite deep. So it requires implementing these sorts of unitaries which are controlled over all these ancillary qubits. So it's a deep circuit controlled over many sort of ancillary qubits. So that is not allowed in the early fault tolerant era. So just a side note, what I mean by this O here is that you're measuring the expectation value of some observable with respect to some quantum state. That's precisely what I mean here. On the other hand, in the early fault tolerant era, circuits of this kind will be allowed. So here you see you have just one qubit as ancilla, and you implement these unitaries controlled on this single ancilla, and the circuit is kind of short depth. So this is what is allowed in the early fault tolerant era. So when I talk about early fault tolerant quantum computers, I precisely mean quantum circuits of this kind, where you don't use many ancilla qubits, maybe one ancilla qubit, you up to one ancilla qubit you can use. You don't have very deep circuits, so you only use short depth circuits. And so much of the freedom that is available to you in the fully fault tolerant scenario or setting is absent here. So the question that kind of motivates this work is can we design useful quantum algorithms using these devices? So recall that in the NISQ era, you could design quantum algorithms, but you did not have provable performance guarantees. So will things be any different when you have early fault tolerant quantum computers? So let's think about it a bit more. So if you want to design quantum algorithms for these devices, what should be the foundational principles behind algorithmic design? Well, you could think of these two principles that I've listed out. So the first thing is that any algorithm that you would design should be looking to minimize the quantum resources consumed. So what do I mean by this? Well, it's better to have T runs of a circuit of depth D than a single run of a circuit of depth T times T. Why is this important? Well, because if you're running a circuit of depth T times D, you would need to maintain coherence for a very long time. Whereas if you're running a short depth circuit, say a circuit of depth D, you only need to maintain coherence for time D. So then you repeat this short depth circuit, say T times, and if you achieve the same task as the circuit with depth T times D, you are good. So this is one of the design principles. You want to run short depth circuits, but you want to run them, say, several times. And these runs are independent of each other. So you can run this short depth circuit, say, once, then you run it again, say, maybe in 2 hours, then you run it again in, say, after 5 more hours, it doesn't really matter because these are independent runs. But nevertheless, the depth of the individual circuits, which is the time for which coherence needs to be preserved, is short. All right, so that's one of the design principles. The other design principle, which kind of distinguishes it from NISC, is that we would like to have performance guarantees. So we would like to have a definitive running time. So we would like to mathematically prove running times of our algorithms, which was really not possible in the NISC era. So for instance, if you look at NISC algorithms like variational algorithms, QAOA, etc., you cannot mathematically prove a running time. So in the early fault tolerant era, we would like to do that as well. So these would be the design principles. So indeed, if you look at recent work, there have been some results on developing quantum algorithms that are tailored to these early fault tolerant quantum computers. And I've listed some references, but most of these algorithms are quite specific to one problem. And that problem is what is called ground energy estimation. So this is essentially a problem where you are given some Hamiltonian and you are supposed to find the lowest energy of the Hamiltonian. So all these early fault tolerant quantum algorithms that I have listed, they are focused on solving this one problem. So in our work, what we ask is, can we implement a generic quantum algorithmic primitive using early fault tolerant quantum computers? So what do I mean by this? Well, I would like to develop a general technique that is broadly applicable to a lot of different problems, not just ground energy estimation, but to a wide variety of problems. This would tell me that, early fault tolerant quantum computers are indeed useful, right? So that's the motivation. So what is that generic algorithmic primitive that we consider? Well, it's linear combination of unitaries. So which is the technique that I mentioned right at the very beginning. So what is linear combination of unitaries? Well, it's a technique where given some Hamiltonian H and an initial state, say at psi 0, then you want to implement those functions of your Hamiltonian to your initial state, which can be approximated by some linear combination of unitaries. So this is basically a very generic statement. So you're given H, you want to implement f of H such that f of H can be approximated by some linear combination of unitaries. Note that a linear combination of unitaries need not be unitary, right? So it's not obvious how you would implement this on a quantum computer. But there are many techniques or quantum algorithms which rely on this framework of linear combination of unitaries. And if you take a look at the literature, indeed this technique of LCU, which I'll be using as an acronym for linear combination of unitaries, has been applied to develop a wide variety of quantum algorithms. So if you look at Hamiltonian simulations, quantum linear systems, optimization, ground state preparation, quantum walks. So for all these problems, you would see that solving that problem boils down to applying a particular f of h. And this f of h, you can see, can be approximated by a linear combination of unitaries. So if I have a generic way to implement linear combination of unitaries, I have a handle over many useful quantum algorithms. So indeed, LCU is a widely applied technique, and it is one of the very few quantum algorithmic techniques that has found such broad applicability. But there's one problem with LCU. Well, the problem is that the standard approach to implement LCU is suitable only for fully fault tolerant quantum computers. So remember how I distinguished between what is allowed in the early fault tolerant era versus what is allowed when you have fully fault tolerant quantum computers? Well, you'll see next that the standard approach to LCU is in no way applicable to early fault tolerant quantum computers. So let's take a look at this technique. So the standard technique to implement LCU. So again, let's recall that the problem of LCU is given some sort of Hamiltonian, a Hermitian matrix, and an initial state. You are supposed to implement some f of h psi 0 such that f of h can be approximated by a linear combination of unitaries, right? And you assume that you want to implement this linear combination of unitaries where you have access to the unitaries themselves, uj, right? Now, throughout this talk, I'll define the total weight of these coefficients as lambda, right? So when I say a linear combination of unitaries, these coefficients are just some real positive reals, okay? So the standard technique works as follows. I mean, you don't need to look at the very details, but what you need to look at and try to convince yourself is that this is really not implementable in the early fault tolerant era. So if you look at the standard technique of LCU, you need log of m, capital M, which I denote by small m, many ancillary qubits. So you need small m many ancillary qubits to prepare some initial state, which is whose amplitudes are proportional to the LCU coefficients, right? And you also need a sophisticated controlled unitary. So this is a controlled unitary which is controlled over all these small m ancillary qubits. And based on this control register, you select the unitary you want to apply. So these unitaries ULs are the same unitaries that are in the description of the LCU, and this is the overall circuit for implementing standard LCU. As you see, this is really not implementable in the early fault tolerant era because you need m ancillary qubits, you need many controlled operations, and you need deep circuits, right? So all these things are not allowed in the early fault tolerant era. So despite this wide applicability, early fault tolerant quantum computers cannot make use of the standard LCU technique. Okay, so indeed, as I mentioned, you need many sophisticated controlled operations and many ancillary qubits leading to very deep quantum circuits. So it's not really implementable in the intermediate term. Moreover, preparing this state, this LCU state, is not interesting. What you would like is to extract some useful information out of the state. So what you would like is to estimate the expectation value of some observable O with respect to this state that you have prepared. Now, this requires even more runs of this deep quantum circuit. So really, it's not suitable for intermediate term. So the problem we solve is basically the answer to this question. So the affirmative answer to this question, rather. So we ask, can we implement any linear combination of unitaries using early fault tolerant quantum computers? Well, the answer is yes. And this is what I'll describe in the next few slides. So how do you develop a new quantum algorithm which is suited for early fault tolerant quantum computers, but it can still implement any LCU. And of course, the advantage is that once you implement any LCU, you can apply this algorithm to develop many new algorithms for useful problems. So then you can automatically say that for most of these problems, you can use early fault tolerant quantum computers to solve them, right? So that's the motivation. So let me zoom into the problem once again. So as I mentioned, if you try to pose the problem a bit formally, so suppose you're given some Hamiltonian H, and we are interested in implementing some function of H, which say is gamma close in spectral norm to some linear combination of unitary. And as I mentioned, without loss of generality, you can assume that these coefficients are positive real. Well, why is that? Because if these are complex or negative, you can express this as some phase, and that phase you can absorb in the description of the unitary itself. So it suffices without loss of generality to consider that these coefficients are real numbers. Right? So this is the problem. So the problem is you want to implement some f of h which can be approximated by a linear combination of unitaries. So what is the problem that we solve? So then the problem that we solve is that we develop a randomized quantum algorithm, okay, which given some Hamiltonian, some initial state rho 0, and an observable O, outputs two numbers, mu and L tilde, right? So what is the significance of these numbers? Well, if you take their ratio, that is, if you take the ratio of mu and L tilde, what you have in the right hand side is that this ratio mu and L tilde approximates the expectation value of the observable with respect to the LCU state. So if you look at this expression, the numerator is just, if you look inside the square brackets, is just the expectation value of the observable with respect to the initial state undergoing this LCU transformation, and what you have in the denominator is the normalization, essentially. So these quantities that the algorithm outputs, mu and L tilde, if you take their ratio, they approximate up to epsilon additive accuracy the expectation value of any observable O with respect to an LCU state. So this is essentially the goal. So this is the problem we solve rather. So for now, for simplicity, let us just focus on the numerator. So note that I mentioned that in the previous slide, the algorithm outputs two quantities, mu and L tilde, such that the ratio approximates the expectation value of an observable with respect to an LCU state. But for simplicity, let us just consider the numerators, that is mu and the numerator, which is trace of O f of h, rho 0 f of h dagger, right? So let's say I rephrase the problem for simplicity, where I'm now just, I'm just, it's my goal is to output some mu such that this mu approximates this quantity trace of O f of h rho 0 f of h dagger up to epsilon accuracy, right? So indeed, recall that f of h is the function of the Hamiltonian that can be approximated by an LCU. So how do we go about estimating the numerator? So the essence of our algorithm is in this slide, which basically, is the fact that if you have to implement an LCU, right? So if you have to implement a linear combination of unitaries, you have the unitaries that you want to implement and the corresponding coefficients that basically are the LCU coefficients, right? So these are the two things that you have. Well, our observation was that you not only have these coefficients, you also have what is the total weight of these coefficients, right? So once you have that, whenever you have an LCU description, you can always define an ensemble. What is that ensemble? Well, this ensemble has the unitaries, these unitaries weighted by this probability, which is the LCU coefficient divided by the total weight of all the LCU coefficients, right? So you can, whenever you want to implement an LCU, which is sum over j, cj, uj, you always for free have access to this ensemble, right? So this allows you to sample unitaries uj according to their probabilities, right? So let's say you do that. Let's say you independently sample v1 and v2, okay, from this ensemble. So what is the expectation value of V1 and what is the expectation value of V2? Well, if you sample V1 and V2 independently, then their expectation values are just sum over J, the probability, and the corresponding unitary, right? So that's just from the definition of expectation value. So if you look at what the expectation values of these sampled unitaries are, if you look at the numerator of this ratio, it is just the LCU, right? So this is the key idea. So that whenever you want to implement an LCU, you get an ensemble for free. And that ensemble is basically each unitary weighted by its corresponding probability that you can get out of its LCU coefficient, right? So that's the first observation. The second observation is as follows. So suppose you, as I mentioned, you sample these two unitaries V1 and V2 independently from this ensemble, right? Now suppose hypothetically, you could implement this transformation, right? So this transformation is not, unitary, right? So you are implementing V1 rho 0 V2 dagger plus V2 rho 0 V1 dagger. We don't exactly know how to implement this transformation, but if you stay with me and assume that there is a way by which I can implement this transformation, then we have something nice, which is the expectation value of this, right? Just by using the linearity of expectation is essentially the LCU applied to your initial state. So that is the second key observation. So I have to find a way by which I can implement this transformation. Okay, then in expectation value, I would be applying an LCU to my initial state. So these are the things that we manage to solve. Let's see how we implement this. So please keep this transformation in mind because I'll be referring to this in the subsequent slides. Okay, so the claim is that this simple quantum circuit, this short depth quantum circuit, is able to implement any linear combination of unitaries. So let's look at this circuit. Well, this circuit clearly has only a single ancilla qubit, right? Which is in the plus state. So plus is just 0, ket 0 plus ket 1 by square root 2, right? So it's in this state. So you have two controlled operations. So this is controlled on 1, which is why there's this solid dot. This is controlled on 0, which is why there's this, hollow dot. So this is controlled V1. This is anti-control, let's say V2. What are V1 and V2? Well, I just mentioned that V1 and V2 are just some unitaries sampled from this ensemble, right? And you know from the previous slide that their expectation values are just, the LCU divided by the total weight of the LCU coefficients. So the other thing in this circuit is this, X tensor O. So this basically says that you are measuring the Pauli X on the first register and measuring your observable O in the second register, right? So that's it. That's the circuit. So you only have a single ancilla qubit. You have just depth 2 essentially, right? So you just implement two controlled unitaries, but they're controlled over a single ancilla. So it's a short depth circuit, single ancilla qubit, but the claim is that this is nevertheless, this can implement any LCU. So indeed, if this claim is true, this would mean that you can implement any LCU using early fault tolerant quantum computers. So let's see if this claim really holds. So what would be our strategy? Our strategy would be to repeatedly run this short depth circuit. We'll show that the output of this circuit, if you run this circuit, is a random variable. And then so each time you run this circuit, you get an outcome, which is a random variable. If you run this circuit enough times, you will get a sequence of random variables such that if you do some classical post-processing, you will approximate the expectation value that you want. That's the idea. So let's see why this works. So let's look at the circuit. If you look at what happens to the state of the system just before measuring X and O, the state of the system is just this density matrix, right? So it's just 0, 0, V2, rho 0, V2 dagger, plus 1, 1, V1, rho 0, V1 dagger, and so on, right? This is just before the measurement. So think about what happens when you measure a Pauli X in the first register, right? So if you measure this ancilla qubit in Pauli X, what happens? Well, this 0 would become a 1, this 1 would become a 0, this 0 would become a 1, and this 1 would become a 0. So what you see is that the off diagonals become the diagonals, and the diagonals become the off diagonals. So what are the off diagonal elements here? Well, my off diagonal elements here are V2 rho 0 V1 dagger and V1 rho 0 V2 dagger. Recall that this is related to the transformation that I want to implement. So if I measure the first ancilla qubit, if I measure the ancilla qubit with a Pauli X, these off diagonal terms will now become diagonal, right? So that when I measure O in the second register, I essentially get this. So this is very easy to verify. If you are not convinced, it's just a 4 or 5 line calculation. You can see that if you measure X in the first register and O in the second register, the outcome is just going to be the expectation of O applied to V1 rho 0 V2 dagger plus V2 rho 0 V1 dagger. This is the transformation that we wanted to implement, right? If you take the expectation value of this quantity, you get expectation value of O with respect to a state that has undergone an LCU transformation, right? So this is the algorithm that approximates the numerator. So we run the above circuit that we've shown, where each V1 and V2 is sampled from the ensemble that I mentioned. So the outcome is a random variable, right? Because I've sampled these unitaries randomly, and the outcome of each run, you store it in some variable, right? Some variable mu j. Then you run this, each time you run, you collect the random variable, and then you run the circuit again and again, and you have to repeat this circuit some t times. We'll come to what t is, but you repeat this circuit some t times, and then take the mean of the samples that you have collected, right? And the argument is that the sample mean is going to be epsilon close to this quantity, the expectation value that you wish to estimate. Why is that? Well, if you look at the outcome after any run of this circuit, this becomes obvious. So as I mentioned, the outcome is a random variable, right? And what is that random variable? Well, it's just trace of O applied to this transformation that we wanted to implement. So if you take its expectation value, by linearity of expectation, you see this V1 row 0 V2 dagger plus V2 row 0 V1 dagger. This becomes just the LCU, the linear combination of unitaries applied to my initial state. Of course, there's this lambda square factor, which comes because of the sampling, because you're sampling the unitaries according to this distribution. And so you compensate for that by multiplying a lambda square here when you calculate the sample mean. So that's essentially the idea. So the interesting thing is that you can approximate the expectation value that you need using much less resources than standard LCO. So as I mentioned, as you can see from the circuit, in fact, that you need only one ancillary qubit, right? So what is the cost of running this circuit? Well, if you look at the average cost, for instance, so suppose the cost of implementing each unitary uj is some tau j, then the cost per coherent run on average is just this quantity. Why? Because you implement uj with this probability, cj by lambda. So the average cost is just sum over j, the probability times the cost of implementing that particular unitary. So that's like the average cost, right? The worst case cost. So the worst case cost is going to be like, so that would be when you are very, very unlucky. So if both times when you sample, you obtain the most expensive unitary, right? That would be the worst case. So let's say the cost of implementing the most expensive uj is some tau max. So then the cost of running this circuit is 2 times tau max plus the state preparation cost, right? So that's basically saying that, okay, you can, each run of your quantum circuit is not much, is much less than standard LCO, because you require only a depth 2 circuit, you require only one ancillary qubit. That is fine. The other question is, how many times should I need to run this circuit so that I can take the sample mean? Well, this is easy, and I think most of you know. So there are very nice results on tail bounds of probability distributions, which tell us when, after how many iterations, the sample mean converges to the true mean, right? So for instance, you can find this out using some tail bounds such as Hoeffding inequality, Chebyshev inequality, etc. So we use those sorts of bounds to exactly calculate what t should be, right? So this is how you approximate this quantity, the numerator of the expression that we had. These are essentially, this gamma is essentially how close your function needs to approximate the LCU. So these are technical details, which is not really that important. What you ensure is that if you repeat this short depth circuit these number of times with probability at least 1 minus some small delta, you output a mu such that mu approximates up to epsilon accuracy the expectation value that you wanted, right? So that's the idea. Now, of course, this was about estimating the numerator, right? So if you recall, the overall problem was estimating mu and L tilde such that the ratio between mu and L tilde would basically give the expectation value of O with respect to the normalized LCO state, right? But this is now easy. Why? Because notice that if you set O to be identity, you estimate the denominator of this expression, right? So if O is identity, this algorithm just outputs the norm of this state, right? So this is the idea. So you run, so the overall algorithm is essentially running this algorithm twice. So first run the algorithm to obtain a sufficiently accurate estimate mu of the numerator. Then you set O to identity. So basically then you will be measuring X tensor identity, right? So you set O to identity, then you obtain an accurate estimate of the denominator and then output the ratio, right? There are some technical details which I'll not focus on too much. You can read the paper if you're interested. So there are some technical details like with what accuracy do you need to estimate mu? With what accuracy do you need to estimate L tilde so that their ratio ultimately gives you what you want with epsilon additive accuracy. So these are just some mathematics that you would need to carefully look at so that everything works out very nicely at the end. But nevertheless, the key idea is that you can implement LCU by running this short depth circuit repeatedly, right? Okay, so this is the overall theorem where, which captures like the correctness of the whole algorithm, right? So again, not very important, these technical details. So if you compare our method for implementing any LCU with the standard LCU, you will find that, of course, as promised, our method has advantages. So if you look at using the standard LCU to estimate the expectation value of an observable, there are many ways by which standard LCU can solve this task. But all of these require many ancillary qubits and quantum circuits of, which are very deep. Nevertheless, these three, we rigorously kind of compare our method with all the possible ways in which standard LCU can estimate expectation values. Here, QAA refers to quantum amplitude amplification, AE is amplitude estimation. So I'm not going into these details in the interest of time, but if you, I'd be happy to take questions if there are any questions that you have regarding these details. But the crux of the matter is, with only one ancillary qubit, which is far less than what standard LCU needs, and with circuits of very short depth, which is like far less than what standard LCU does, we implement LCU, right? Of course, what we pay is we need a few more classical repetitions. But this is fine because recall, in the early fault tolerant era, what you want is to minimize the coherence time, right? So that means you would like to have short depth circuits. It is fine if you take many independent runs of this short depth circuit, right? All right. So what I just described was a general technique to implement any LCU on early fault tolerant quantum computers. Now recall that I said that LCU is a broadly applicable technique and it has many different applications. So if I have an algorithm for implementing LCU on early fault tolerant quantum computers, I can also apply them to various problems of interest and develop quantum algorithms for all these problems that are suited for early fault tolerant quantum computers. So here in this paper, I focused on three such problems. One is Hamiltonian simulation. The second is ground state property estimation. And the third is quantum linear systems. So what is Hamiltonian simulation? Well, you're given some Hamiltonian H, some initial state psi 0. What you would want is to estimate the expectation value of some observable O with respect to the time evolved quantum state. Right? So that's the goal of Hamiltonian simulation. Ground state property estimation is that you're given a Hamiltonian with an unknown ground state. You want to estimate the expectation value of some observable with respect to the ground state of that Hamiltonian. And quantum linear systems is, you're given some Hamiltonian, some initial state. You would suppose this state ktex is basically H inverse applied to this quantum state appropriately normalized. Then we would like to estimate the expectation value of an observable with respect to this state X. Right? So these are all useful problems that have found applications in many different places, and all of these rely on LCU. So for each of these tasks, we apply our generic LCU technique to develop new algorithms, and all these algorithms are suitable for early fault tolerant quantum computers. So let us look at the first application. So Hamiltonian simulation. So again, suppose you're given some physical Hamiltonian. So by physical Hamiltonian, I mean that your Hamiltonian is a linear combination of strings of Pauli operators. So by a string of Pauli operators, I mean tensor products of Paulis essentially. And some initial state. So we apply our LCU method to develop a randomized algorithm that outputs some mu, which approximates the expectation value of an observable with respect to the time evolved quantum state. And so if you look at the complexities of our algorithm, I don't go into the details of the algorithm in the interest of time, but if you look at the cost of each coherent run, that is the circuit depth, it scales with the total weight of the coefficients of the Hamiltonian squared t square, and it only has a log dependence in the inverse precision. And these are essentially the number of classical repetitions you would need to approximate the expectation value. So you can, of course, compare our Hamiltonian simulation algorithm with the state-of-the-art Hamiltonian simulation algorithm. So of course, I'm not going to go into the details, but if you look at other near-term Hamiltonian simulation techniques, these are first-order Trotter methods, Q drift. Our method has exponentially shorter circuit depth. So if you look at the circuit depth of these methods, they depend on 1 over epsilon, whereas in our case, it depends on only logarithmically in the inverse precision, right? So it's log of 1 by epsilon, whereas these depend on 1 over epsilon. Whereas on the other hand, if you start looking at state of the art, the best Hamiltonian simulation algorithms, they require a lot of ancillary qubits. And of course, they require deep circuits, right? So we have kind of the best of both worlds. So for with respect to the state of the art Hamiltonian simulation techniques, if you compare the time of our method with these methods, there are regimes where our method has an advantage despite requiring only one ancillary qubit, whereas these other methods, these other near-term methods, require many ancillary qubits. So how much time do I have? Anindita, if you could just tell me, then I'll tailor my talk accordingly.
So maybe 5 minutes?
I have 5
Is it
minutes.
okay?
Okay. Yeah,
Okay,
that's fine.
okay.
That's fine.
Fine.
That's fine. Okay, so we also apply it to ground state property estimation, where again I don't want to go into the details. The story is the same. You can since this is a problem that can be solved by LCU, we apply our algorithm to this problem and find advantages, right? So the advantages in terms of the number of ancillary qubits needed, the circuit depth required, etc. The same with quantum linear systems and so on. Now, in this paper, we also introduced 2 other methods of implementing LCU. So one of these is called the ancillary-free LCU. So in the previous method, I mentioned that we require only one ancillary qubit. So in this method, what we show is that there are scenarios where you can get away without using any ancillary qubits at all. So when can you precisely do this? Well, this is precisely the scenario. So suppose you prepare some quantum state by LCU, right? And what you're interested in is the projection of this quantum state in some subspace of interest. So that is, say, what you're interested in. We show that if this is the case, then you can do away with all ancillary qubits. So here what you do is you just sample from this ensemble, and you get some average density matrix, right? Which you get by applying the sampled unitary to your initial state. And then what we could prove is that the projection of this average density matrix on this subspace of interest is at least as large. Okay. So this is very interesting because this is precisely the scenario for many quantum walk problems. Suppose you have a graph where you are interested in finding or hitting some marked nodes of the graph. So there you're interested in finding the overlap of your state with this marked subspace. And it is fine if you can show that that your algorithm succeeds with at least some probability, right? Some constant probability. So in such scenarios, previous algorithms used LCU, but they required many ancillary qubits because they were using standard LCU. But we showed that you can improve the efficiency of these algorithms in terms of the number of ancillary qubits needed, in that you don't need any ancillary qubits at all and still retain optimal complexity. So these are some of the findings which I'm happy to discuss later. The last thing that I would mention is a third technique which might appeal to physicists. So recall the discussion that we were having is what comes between NISQ and the fully fault tolerant era. So one of the possibilities that I mentioned early on is the so-called early fault tolerant quantum computers. Well, this is not the only possibility. There's another possibility. There are many other possibilities, of which one is the so-called hybrid qubit Q-mode systems. So many quantum technological platforms like ion traps, superconducting qubits, they have access. So in these systems, you have access to continuous variables, right? So the idea is that if you couple a discrete system to a continuous variable system, then you can engineer, then these interactions can be engineered for long time scales. So people believe in the intermediate term, these hybrid qubit Q-mode systems can implement meaningful quantum computation. So what we show also in this paper that you can leverage these hybrid qubit Q-mode systems to do any linear combination of unitaries. The idea is very simple. So suppose you have a system, discrete system H, and you couple it to a continuous variable system. So you couple it to a continuous variable system. Suppose it's the interaction Hamiltonian is H tensor Z, where H is the discrete system and Z is, say, a degree of freedom of, say, your harmonic oscillator, right? So quantum harmonic oscillators, degree of freedom could be position or momentum, does not matter, some degree of freedom. So then you prepare this system, the discrete system, in some state psi, and the continuous variable system in this particular state, and then you evolve the system according to this interaction Hamiltonian, right? And then what you can show is that if you just after some time of evolution, if you post select on the continuous variable system, you end up with what is an LCU in the first system. So of course, the important thing here, you should be able to prepare this state efficiently, right? So that is the key catch here. And what are the quantum states that are efficiently preparable in continuous variable systems? Well, it's Gaussian states. So indeed, we show that using these Gaussian states, you can implement many different kinds of LCU. So one example is ground state preparation. So what you need is essentially to prepare your discrete system in some initial state psi, your continuous variable system in a Gaussian state, evolve the resulting system according to this interaction Hamiltonian. And what you see is that you implement a particular function of the Hamiltonian, which helps you in preparing the ground state. The same concept can also be used to implement solve quantum linear systems, where both. So you use two ancillary continuous variable systems, both of which are prepared in the Gaussian state, and again you let this interaction Hamiltonian evolve this interaction Hamiltonian for some time. What you see is that you implement H inverse, which is your linear systems. So these are the three techniques essentially that we introduce in our paper. And this is a summary of the results. So each of these three techniques, they are focused on implementing this broad technique LCU on intermediate term quantum computers. And of course, we've been able to do that, which has allowed us to find many applications for these intermediate term quantum devices. So that I'll stop here. Thank you very much. And I'd be happy to take questions.
Okay, thank you, Shantanav, for your wonderful talk. Any questions from the audience here?
Yeah, I have a few questions.
Yes.
Okay, continue, please.
Can you hear me?
Yes. Yes, I can hear you. I can hear you. Yes.
Okay, so maybe I missed like the function f of h. You can write as several combination of unitaries.
Yes.
So
yes.
combination Cj Uj. So in general, it is not unique. So, but you are saying the depth m. So which combination, linear combination you choose?
So you mean for the standard LCU technique, or the algorithm that I propose?
Yeah, tell me for both. Like.
Okay. Okay. So if you look at the standard LCU, so your goal is to implement some function. Sorry, just a second. I can't see my mouse. Okay, let me just pointer options, laser pointer. Yeah. So you want to implement some function which is a linear combination of these unitaries, right? So there are m of them, let's say. right? So then in the standard LCU technique, you would have to implement all M unitaries controlled on these many ancillary qubits, right? So there's no getting away with it, right? You just have to implement all these M unitaries. So that's why I said that the depth is, at least M, right?
Okay.
And in the method I mentioned, what you do is you can get away with depth too, because what you do is you sample a unitary, okay, from this ensemble. So you have M unitaries in this ensemble, but you sample unitary uj according to this probability, right?
Okay.
So you sample two unitaries and then put them together and form your quantum circuit. So at any point, your quantum circuit has depth 2 instead of M.
Yeah, but I'm asking in the first place. So when I write the function as a combination of Cj, Uj, so this combination itself is not unique. So I can have several such combination, right?
Right,
So
right.
shall I choose the combination where the number of unitaries is less, or some it is
Yes, right, right. That's a good point. So typically, the people look at the problem the other way around. So people, what people do is, the target is to implement some f of h, and you want to find the, the linear combination of unitaries where the number of terms is less, let's say. So that's the goal.
yeah, but
So there
sometimes
are
it can happen like the number of unitary is small, but the particular unitary is difficult to implement. So, for
that
example,
may
suppose
also happen. That may
like
also
what you
happen.
are saying about continuous variable. So, in some case, I get like the permutation and Fock basis, but in some way, I get like some unitary which is easy to implement. So, I think that will depend on the physical problem you are working also, right?
Absolutely, absolutely, absolutely. So the general technique that I mentioned for linear combination of unitaries, well, that poses the problem as a general problem. Then when you move on to the particular applications, so what you are mentioning are the considerations, right? So okay, what kind of linear combination of unitary would be easy to implement? How does it depend on the total number of terms?
Yeah,
Which
in
description has,
principle there is infinite combination.
of
Like,
course, of course.
yeah,
But for instance, in many cases, what you can show is that even if, say, for instance, let's take the worst case. Let's say you have a linear combination of unitaries where the number of terms is infinity.
no, I'm not
Then
saying the number of time is infinity, but I'm saying the way I can do this linear combination. There are infinite ways.
yes,
Let's
that
say
is also
I'm
true.
taking finite unitary, finite number of unitary, but the ways are infinite.
Right, right. So then you choose the description where these UJs are, easily implementable, right? Or are the easiest to
Yeah,
implement.
actually
That's the
okay.
goal.
Okay, and the second thing, so like the number of ancilla you need, this is for like two cases. One is when you are applying some gate, you need ancilla, and other is some when there is some noise, you want to correct the noise. That's why you need ancilla.
No, so here I am not considering any noise.
Yeah,
Here,
that's I'm actually asking. Like there are two ways and answer. So
uh,
when like running for the circuit for like one run with higher depth, and you are dividing it with multiple runs with lower depth, so and that's why you can implement with like two unitaries and only one ancilla, one control.
yes, yes.
So what I'm asking, like if I do this under same noise model, so do you expect that the rate of error or the error will be more in like in your case or either? Like can
So,
you some
so that's
idea
a
if you
good question. So intuitively, I would say that
like
since
actually one advantage you are getting, so I'm asking like is there any trade-off? Like when you are getting some advantage, do you have to sacrifice something like or not?
yeah, so the trade-off is not in the noise. So if you look at the circuits, if the circuit is short depth, so that means you'd have to preserve coherence for shorter time. So
Yeah.
the effects of noise is going to be less here because you're maintaining coherence for shorter times. So I would expect that this is going to be more noise robust than,
Yeah,
say,
but
the
when
other.
you do in different run, so the
Yeah,
accumulated error, so actually, I know it is difficult, but intuitively, any idea like in which
yeah, yeah.
case the error rate will be less or something?
Yeah. So there are two things. So first, let me answer. The second half of your first question is what do we pay, right? Because we are
Yeah.
doing short depth circuits. So if you look at this, um, so what we pay is you have to make slightly more classical repetitions.
Okay.
So you need to make many more runs, but this is fine because these classical repetitions are independent of each other. You can run this short depth circuit on say at 10 a.m. Then you can take the second run at 10 p.m. This is perfectly fine because these are completely independent. But
Yes.
every time you do the run, it has to be of a short depth circuit.
Hmm.
So of course we pay a bit more in terms of classical repetitions, but as I mentioned in the early fault tolerant era, this is not a problem as long as the runs are independent of each other. Whereas if you look at standard LCU, they need to have a deep circuit with just one kind of run of this deep circuit.
Okay. Okay. Yeah, actually, very interesting talk. I will look into the paper, and I also
Thank
plan
you.
to visit sometime IIIT Hyderabad.
Oh, you're most welcome.
Yeah, actually, I have a lot of friends there.
Oh, you're most welcome. Just drop me an email. I would
Yeah,
be happy to host you.
thank you for the nice talk.
Okay, any more questions from the audience? Okay, I think Amrita has one question.
Hi, Shantanav, good to see you here.
Hi.
Hi. So, I have some small questions. First of all, whenever you are approximating your FS functions as the combination of the unitaries, so in most of the cases, the results are like this is the exponential of the Hamiltonian or H inverse or H transpose. So, is it possible with the polynomial case, or is there any result?
What do you mean by the polynomial case?
A polynomial of the Hamiltonian, I mean, say I plus h square or something like that.
So if you want to implement any polynomial of your Hamiltonian, right? So if you want a technique where you want to implement any sort of polynomial of your Hamiltonian, I don't think that LCU suffices. There you would need what is called quantum singular value transformation. But still, for many different matrix functions, you can show that they can be approximated by LCU. But I won't say that you can implement arbitrary polynomials or arbitrary polynomials of the Hamiltonians may not be approximated by LCU.
Acha, is there any specific structure for this matrix polynomial you are talking about? So, is
Yes.
there any existing result for that?
Yes. So you have to look at. So this paper is called Quantum Singular Value Transformation by Andras Kilian, Yuan Su, Nathan Bebe, Guangho Lo. I'll send you the paper. I'll send you the paper.
Okay.
So that is a
Uh,
general technique by which you implement polynomials of Hamiltonians essentially, or
Okay, to make the bound, so you have usually used the spectral norm. So is it basically you are doing with the unitaries, or is there any advantage over the two norm or any other
no.
norms?
I
Yes.
mean, there's nothing specific about it. Nothing specific
Okay.
about it. You can take your
So we
favorite
can
norm.
go further with other norms as well here. Okay.
Yes. Yes. You mean for
And
this one, right?
yes, for
Yeah.
this one.
Fine.
Mm. And is there any second thought for this gamma or any betterment of this gamma bound, or are you
You
looking
mean
for this one?
this gamma?
Yes. I mean,
I don't think this can be improved for the technique that I mentioned. I think if you look
hmm,
at the calculations, they are pretty tight in the because this analysis is very general, right? I mean, it assumes very little. I mean, I am talking about any function that can be approximated by a linear combination of unitaries. That is, it is gamma close in spectral norm, right? That's what I say. For this, I don't think you can improve this by much. This gamma.
okay.
Because of course, look, if you think about it, you need epsilon by norm O, right? Because you are making norm O square by epsilon square classical repetitions, right? You also need epsilon by norm of f of h because you're trying to approximate a quantity where f of h comes, right? You're basically trying to approximate this over these many repetitions. So whatever dependence you have on gamma has to have epsilon by norm O times norm h. So the only thing you can hope to improve is this 18. You can
Yes.
maybe
So
improve it
that will
slightly,
not
maybe, I
affect
don't
too
know.
much. Yes.
No, by a constant factor, right?
Mm.
So it will
Hmm,
affect
hmm, hmm.
everything by a constant factor.
The next one is that I didn't get that string of polynomial operators where you have taken that
A string
this
of
one.
not polynomial operator. I see what you're saying. So it's a string of Pauli's. So this one probably, isn't it?
Sorry,
Am I
sorry.
right?
Yes,
Uh-huh.
Pauli operators. Yes.
Yeah. So think about this as, say, this is, so let's take PK. PK is, say, identity tensored sigma Z, tensored identity tensored sigma X, tensor. So this thing I'll call a string of Pauli operators.
So, is there any dimension specified for that? That how many tensor you are taking here?
Yeah. So
So,
this is an n-qubit Hamiltonian, right? So this is an n-qubit
okay,
Hamiltonian
okay.
of L terms. So yeah, I should have been a bit more precise about, like, given an n-qubit Hamiltonian, etc. But yeah, this is an n-qubit Hamiltonian. So you take tensors of these Pauli's and identities, but of course, the dimension has to be 2 to the n.
Okay. And from this single analog and ancillary one, so which one perform better from your perspective? I mean, which
So
one
you
is
mean
the
among the three? Among the three,
Yes,
you
yes.
mean? So depends on the problem you want to solve, right? So this is
Okay.
really for gate model quantum computers, right? So for circuit model quantum computers, and this is applicable for any LCU, right?
Yes.
If you look at this one, ancilla free. Okay, let's talk about analog LCU. Well, analog LCU is for this hybrid qubit Q mode systems, which is a different architecture, not really the gate model, but where you couple a discrete system to a continuous variable system. So it's a different quantum technological platform for implementing LCU, right? Now, ancilla-free LCU, you can have ancilla-free LCU here in analog, right, in hybrid qubit systems, or you can do it in the gate model. But it is restricted in the sense that it only works if you are interested in the projection of an LCU state in some subspace. So if that is your goal, you want to find, you want to prepare some state by LCU, and then you want to project that state in some subspace, right? Let's say that is what you want to do. If that is your task, then, so for instance, in quantum walks, this is what we do often. You must be very familiar with those. So in such cases, so if you look at, say, quantum fast forwarding, right, by quantum walks. So there, what do people do? I mean, you implement an LCU, right, at the end of the day. And you implement an LCU and you prepare some state and you project that state on some marked subspace, right? So that
Yes,
is
yes.
what I mean. So in that case, what we showed is that you don't need to perform an LCU at all, right? Like with all these ancillary registers and so on. You just need the walk space and just random sampling. That's it. So that is where you can use ancillary LCU. So the
Okay.
settings in which this can be applied is a bit different. Yeah.
Okay. Thank you.
Thank you.
Okay, but for our online viewers, if you cannot unmute your microphone, you
Hello.
can just type the question or you can ask. Who is there?
Yes, I have a question.
Yes,
Yes,
please.
go for it.
Yeah, so the Hamiltonian was approximated, or the matrix, Hermitian matrix was expressed as a linear combination of unitaries. And then from
Oh.
those unitaries, an ensemble was created, that D, and then from that ensemble, two were randomly sampled. And then the short depth circuit was created, right? So my question is, we are sampling here only two unitaries, V1 and V2 are sampled from that whole ensemble. So how is it ensured that the full information of the H that is present here? Because it can be if we are running this circuit again and again. So if we each time are we using different V1 or and V2, meaning each time are we sampling again and again?
Yes. So good question. So first of all, you probably mean f of h. So h is not approximated by a linear combination of unitaries. F of h is approximated by a linear combination of unitaries. And
Yes, sir.
so the idea is in each run, you sample V1 and V2 independently. So every time you run this circuit, you sample, you obtain V1 and V2 by sampling from this ensemble, and then you run this circuit. So each time, what is the output of each run? Each run is a random variable, right? Now, all this guarantees each run of this circuit is that the expectation value of the random variable is basically giving you what you want. So of course, all the information is contained in the expectation value, not in the individual random variables. That's the idea. So if you collect enough random variables, right, each of which has the same mu, right? So you know that if you take the sample mean of these random variables, if you take enough number of samples, they will converge to the true mu. And true mu is what you want to estimate, right? So that's the idea. So each run does not contain information of the whole thing, but in expectation value, it does.
So we are sampling here randomly. So can we sample it using some other technique so that with shorter number of runs, we can go to the closer value of the mu? Because if we do randomly sampling,
I don't think,
then we need to do many number of run more.
No, I don't think so, because you're randomly sampling in the sense that you need to sample uj according to pj, right? This has to happen if you want in expectation value to this for this to hold. If you do sample from some arbitrary distribution, this won't hold anymore, right?
Okay. Okay.
And this is easy to do because all you need is, each uj is indexed by this integer j. So all you need is to sample some integer j according to this probability. And because there's a bijection between this integer j and unitary uj, you're done. You know which unitary to implement. So you run your classical computer to get these integers and then implement the corresponding circuits.
Okay, sir. Thank you.
Thank you.
Okay, I think in the chat, Akash Kumar has some questions, but I think he said it is clear now for him.
Okay.
But maybe you can just okay, I think this is fine.
Okay, then I'll need to stop sharing my screen because I cannot read the chat without.
Yes. Okay, fine.
Okay, I'll stop sharing then.
It is clear from my side. I got it. The last answer that you given.
Okay.
Okay, I mean, I have a very small question that, I mean, is there any range for this gamma one, or, I mean,
you mean
is there
gamma?
Yes. Is there any range for it, or?
So you would want okay. Let me go to the full theorem.
Mm-hmm.
You would want the function that you want to implement, right? Of your Hamiltonian to approximate the LCU up to some gamma accuracy. So you would want gamma to be upper bounded by this. So that is its range.
Okay.
So of course it can't be negative, right? It has to start from 0. So if it is 0, well and good, right? That means it's a perfect LCU. But otherwise it needs, so you need to find an LCU description of your f of h, which is gamma close such that this gamma is at most this. If it is farther away, then that's not a very good LCU description.
Okay,
That's
and this mu and L tilde. So mu is the stress of observables, right? With respect to this.
Yeah. So the mu, you can think of mu as approximating this new. Okay, let me just.
This one and L tilde is this one, but okay. So if you take the ratio, it will always depends on the ratio.
Yeah, so you would have to estimate this. So mu estimates this, L tilde estimates this. So what you do is you estimate this to some accuracy. You estimate this to some accuracy. But you have to do that cleverly so that when you take their ratio, what you get is epsilon accurate, right? So these are precisely given here. So you need to estimate mu with this accuracy, estimate L tilde with this accuracy, and then you can prove that mu by L tilde will approximate what you want with epsilon accuracy, essentially.
I see.
Yeah.
Okay, any more questions from the audience, from the online viewers, or from here? Okay. Yes, please continue. Yes.
Sir, how you are fixing the number of ancilla? I mean, in some cases, say you take 1 or 0. I mean, how?
Oh, no. I have not taken 0 ancilla. I've only taken 1 ancilla, right? If you look at my algorithm, it has 1 ancilla, right? Was I clear or so?
Yeah, in the table.
Oh, table. So these are other methods. So okay, I see what you mean.
Yeah.
Let's take this one. Yeah, these are other techniques, not my algorithm. So if you compare it with, say, other techniques, there are some techniques which do not require any ancilla. So these are Trotter methods. So they don't implement. So this is for Hamiltonian simulation. So there are many techniques to implement Hamiltonian simulation. Some are suitable for near-term quantum computers, some are not. So if you look at the, some of these near-term methods, say Trotter method, Q drift, higher order Trotter, they don't need any ancilla qubits. If you focus on this incoherent row, they don't need any ancilla qubits. But what happens is that their circuit depth is quite large. So if you look at their dependence on epsilon, it's 1 over epsilon, whereas in our case it's log. So that is what I meant. And you can ignore this part, this coherent part. Here I'm saying, okay, they could also use quantum amplitude estimation to coherently estimate the expectation value, but that would increase the number of ancillas. But this has nothing to do with my algorithm. This has to do with other methods.
Okay. Thank you, sir.
Thank you.
Okay, any more questions? Okay, if not, then let's thanks our speaker. Thank you, Professor Shantanav, for your wonderful talk. And so we are now closing the session. So thank you. Thanks a lot.
Thank you, everyone.
And okay, you can visit here. I mean, anytime if you just want,
Of course.
Send me an
And
email. And
yeah, and
you are
same
always
goes for
welcome
all of
here.
you. Yeah.
Yes. Okay. Thank you.
Bye.
Okay. Bye, everyone.